Hello students, so welcome to today's lecture. As we discussed in the last class, the use of UV visible spectroscopy for understanding the DNA. Now, in detail, although I have discussed this, but in detail today I am going to use the concept of UV visible spectroscopy for proteins. Now, why proteins? If you look at the protein, not only in our fundamental basic research, but also applied research and also in industrial setup, the proteins are one of the major therapeutics, right? Peptide based therapeutics, monoclonal antibody based therapeutics, protein based therapeutics. In the therapeutics, also enzymes, those are also protein for many enzymatic application. You require such a quantitative tool which is easy and easy to handle and like a reproducible. In those cases also UV visible spectroscopy is significantly used. Therefore, understanding this basic and simple technique, how we can use that for industrial application also is very important. And many people actually, though it's a fundamental technique or very basic technique, many people have don't clear understanding of application of UV visible spectroscopy or absorption spectroscopy to study the protein, their structure and quantitation and all those. So, today little more detail I am going to explain so that your concepts are matured, right. So, this module what we are going to again touch up upon theory, practice and clinical and as well as the industrial application of UV visible spectroscopy for protein characterization. So, remember we had already discussed the basics of that, Beard number law, the concepts of chromophore, the extinction coefficient and the amino acids such as the aromatic amino acid which contributes to the UV visible spectroscopy. We saw its application in like protein concentration dependent and also for purity assessment. Subsequently, we looked at the thermodynamics associated with proteins. We quantified the Gibbs free energy, the enthalpy associated with that, entropy associated that and the stability which is governed by this melting temperature Tm, and also we did some Bonhoeffer analysis, and this can be used, all these concepts of thermodynamics predicting the protein stability, right, and optimizing the storage condition. So, you see you produce protein, but you immediately do not use it, right. You have to have a storage condition, your protein should be stable. Many of the industrial application happens at high temperature. You require to have a stable enzyme that can work at 55 degree, not at like a 25 degree or 4 degree. Typically in our research lab, we all the time keep protein on ice, right, so to retain its activity, but industrial application you cannot do that. So, you have to have a protein which is stable at variable temperature, higher or lower temperature, and we need to also a storage. So, what is the safer condition where we can store protein but without losing its activity? Those are the practical application of understanding the thermodynamics of protein. Then third concept is important, which is the unfolding rate, right. So, how protein folds, unfolds, associated with that Arrhenius equation, the refolding pathway, multiphase kinetics, denaturation profile that has to study. And this basically practical application is protein stability, industrial process optimization, so that you do not lose your protein in this process. So, kinetics is also important. Now, denaturation strategy, like how you denature the protein. So, you can heat up the protein for denaturing, that is called thermal denaturation. You can add urea or guanidinium hydrochloride, that is a chemical denaturation. You change the pH and pH dependent denaturation is there, and associated with that we had seen hyperchroism and microenvironment effect, and this helps in characterizing the protein behavior under various conditions. Finally, we are going to touch upon the clinical application, right. So, clinical or say industrial or biopharmaceutical application. So, you know many of the monoclonal antibody, which is the prominent modality of therapeutics, the MABs, this technique can be used for quality control assessment, right. The biomarker quantification can be used, point of care diagnostic can be used using the simple concept of ELISA or digital ELISA can be used, and this helps us in real world diagnostic or therapeutics development, right. So, today we are going to touch up upon some of these important concepts and how these concepts is going to be used in therapeutic setup or industrial setup or even in the clinical setup. So, in this class and probably in next class we will be continuing that. So, just to brush up your memory, we have seen UV visible spectroscopy is an essential analytical technique that measures the absorption in the ultraviolet region as well as the visible region. So, somewhere say if we tell it right 190 to 1100 nanometer, and this is by proteins, and that is helpful in providing the quantitative and qualitative information about the protein concentration, its structure, it is a biochemical application. So, what we call it, this is far UV right 190 to 230, then near UV 250 to 320 and then visible 320 to 1000, right. What absorbs, what is the chromophore here in the UV region, this N to pi A star transition, pi to pi A star transition, and this basically tells you about the secondary structure and backbone geometry. The typical ellipticity is 5000 to 7000. Then in near UV, which is used for tertiary structure of the protein, the chromophores are aromatic amino acids such as tryptophan, tyrosine, phenylalanine, also disulfide. This tells about tertiary structure of the protein or microenvironment of the protein. So, if you look at near UV and far UV tells you about secondary and tertiary structure of a protein, right, and the extinction coefficient is low. So, absorption here is quite high when we look at in the far UV region, but here signal is low and therefore requires, for getting the tertiary structure of protein you require high concentration of protein, right. The third one is the visible region where like a heme group or flavine group or metal center, that prosthetic group absorbs, and this is cofactor binding or redox state of protein you can determine, and like this ellipticity is variable typically, right. So, this is something that already we have seen. Here are our UV visible range. This is for IR, this is for microwave spectroscopy, this is for NMR, then X-ray and gamma ray, all we have seen it, right. So, if we compare with other techniques, you require, right. So, UV visible requires the minimum volume. If you compare say UV visible with HPLC, with mass spec, with NMR and X-ray. So, the volume is typically on a lower side. The analysis time is really fast, less than 2 minutes or 5 minutes, whereas other techniques takes longer time. The equipment cost is cheaper, right. So, compared to other techniques this is cheaper, it is non-destructive. So, you can use same sample for doing another thing. NMR is again non-destructive, whereas HPLC and mass spec are not non-destructive. Now, the quantitation is excellent, right. So, HPLC is slightly lower, but you can use that also. Mass spec is excellent, NMR is excellent, and X-ray you cannot do much quantitation. Structural information here, although it is a lower volume, cheaper, but you have a limited structural information, and NMR you can get a very detailed information. Similarly, X-ray you get detailed information, but good part that this is a very high throughput, right. So, in 96 well you can do, whereas the detailed structural analysis either using NMR or X-ray it is a low. So, key advantage for clinical proteomics or clinical application, it is a rapid technique, non-destructive analysis, you require really minimum sample preparation, it is a cost effective and high throughput, and in real time you can monitor the protein dynamics and stability, and you can use this for point of care diagnostics, and translation can be done for point of care diagnostic, right. So, yeah, that is the good part of UV visible, that compared to other technique, that it is a fast, low concentration, cheaper and quantitative, but information that you get is limited. Already we have seen, so what we measure is absorption, which depends upon the path length and concentration, and this is fixed for particular sample. So, this is molar ellipticity, and then you can we have also seen that absorbance can be converted into transmittance, and range we can find it out. So, what range, it is a linear, that we have seen it. So, here is some quantum mechanical formalism coming up to the like when we want to derive the absorption. So, delta E equal to h mu, which is h c by lambda, and Beer-Lambert's law emerges from delta I by delta x is equal to absorptivity like alpha I. So, if you arrange that and taking the logarithm, what we found, that log base of 10 I 0, which is the initial incidence light, by I equal to E C L, and that is this one is absorption. So, that is what we have, E A equal to E C L, coming from the basic concepts of how much light we put it, how much light emerges out, and how much gets absorbed, right. So, that is what we do, the practical concentration and limitation of UV visible. When the concentration while like is low, the deviation is 10 to 50% at 1.5 millimolar, and this basically can happen because of protein aggregates or excluded volume. The path length that we are going to take is basically the shorter path length. Now, deviation can happen above 50%, below 0.1, and light scattering dominates in those cases. So, this is the practical concentration. So, what is the validity range for the concentration here? So, maximum 1 millimolar one can get, path length maximum 10 centimeter you can get, and deviation can happen if there is a like if 1.5 molar we are going, the deviation can happen 10 to 50%, and that deviation can be causing because of say protein high concentration, protein aggregation can happen, right. Path length, if you are going more than 10 centimeter or below this, then deviation can happen below 0.001 centimeter, 50% deviation can happen. This is happening because of light is not passing through, it is a scattering. The wavelength, it is a validity range is between 290 to 900, and then 10-20% extreme of those can again deviation can happen, and the baseline drift can happen, photomultiplier noise can happen. Now, pH validity range should be plus minus 0.5, the deviation can happen if you change that, and here because of ionizable residue are coming. Temperature 0.5 degree centigrade, and then 2-3% can change, and this is thermal expansion and molar mode. So, there is a range where we can operate while doing the UV visible range for each of these: concentration, path length, wavelength, pH and temperature, right. So, that is the thing. So, for any protein, the extinction coefficient you can calculate at 280, this is how many tryptophans are there into extinction coefficient of tryptophan, how many tyrosine are there, N is a number of tyrosine, into extinction coefficient of that, and how many disulfides are there, extinction coefficient of that. So, this you can put it out, and that is what we can find it out, extinction coefficient for any particular protein. So, for an example, let us take a BSA, it is a 66 kilodalton protein, it has 2 tryptophan, 20 tyrosine and 17 disulfide. So, you can put 2 multiplied with 5500, 20 multiplied with 1490, 17 multiplied with 125. This is the molar extinction coefficient coming, and a specific molar extinction coefficient, you divide this number which has come by the molecular weight, and that unit will be ml per mg per cm, right. The molar extinction coefficient per mole per centimeter, here ml per mg per cm. So, that is the specific molar coefficient, specific extinction coefficient, and this is molar extinction coefficient, right. So, now what are the chromophores? of protein in near UV region. So, aromatic amino acid essentially that are the intrinsic chromophore like a tryptophan or tyrosine or phenylalanine. In these, if you look at in tryptophan, there is an indole ring, right. In tyrosine, it is a phenol ring, or here the benzene ring, and this is the lambda max for this of 280, tryptophan 274, tyrosine, and 257 to 258, it is a phenylalanine. This is the molar extension coefficient of this. The pKa is this, and then prevalence is 1 to 2%, 3 to 5%, 4%, right. So, key features, that is the highest molar extension coefficient, sensitive to the environment. Therefore, when we go to the fluorescence, we will see that this is the best intrinsic fluorophore we have, because it is sensitive to the microenvironment, and that gives the idea about tertiary structure as well in fluorescence. But in near UV also you can get the idea about tertiary structure. Now, tyrosine, it is a pH sensitive, but ionizable 11 or 10 it can ionize, and here it is a molar extension coefficient is lowest, and that is rarely used. So, dominant chromophore in the near UV region are tryptophan and tyrosine, right. So, let us see what are the absorption mechanism, just bring little bit of quantum mechanical concept. So, tryptophan lambda max we saw at 280 nanometer. Now, transition type happens pi to pi star, that is HOMO to LUMO, right. Chromophore is here extended indole ring conjugation, and it is a highly sensitive to polarity. So, a stock shift can happen, and that we are going to look at when we look at fluorescence. The structural role is hydrophobic core indicator. So, tryptophan generally buried inside the protein, and therefore, it is used for understanding the stability marker. Now, tyrosine, essentially the transition happens again pi to pi star, it is a aromatic HOMO to LUMO, and here it is a ionizable transition happens when it goes to high pH. The phenolic OH can go to phenolate, that is O minus. Now, neutral form lambda max is 274 and extension coefficient is 1490, the ionizable pK 10. Now, coming to third one, which is phenylalanine, it is a weak one, right. So, it absorbs around 257 258, it is a weak chromophore, therefore, extension coefficient is low, generally ignored in protein concentration quantification, and relevant only in the protein with high phenylalanine content and low tyrosine tryptophan. So, wherever there is no tryptophan tyrosine, we use or rely upon phenylalanine, otherwise tryptophan and tyrosine are dominant one. Now, what is the absorption spectrum characteristic? Lambda max 278 for aqueous or exposed in this case, and 278 if we are coming, this is coming from protein interior, that is partially buried, and hypochromosity we can find it out 20 to 40% reduction because of aromatic interaction present. The tyrosine, as we saw, that is a pH dependent, right. So, OH to O minus. So, fraction of alpha like ionized can happen, that is fraction ionized, and at 7.4 99% neutral, at 10 50% ionized, and 12 99% absorbed. So, if we are changing the pH of a protein where tyrosine is there, this factor has to be also considered, right. So, at 280, when typically for protein concentration, when we measure the concentration of a protein, you see these are the 3 amino acid or 4 groups that are contributing, but dominant contribution comes from tryptophan. So, 60 to 80%, then 20 to 40% comes from tyrosine, and then 2% from phenylalanine and 1 to 5% from disulfide, right. So, it is a negligible at 280. This contributes to secondary structure, and dominant contributor coming from tryptophan, right. So, after looking at these chromophore and their contribution to understand the secondary structure, tertiary structure, and estimating the protein concentration, let us look at how the environment effect on absorption happens. We have seen this term hypochroism and bathochroism, right. So, reduction in the extension coefficient when aromatic chromophore are in close spatial proximity, that is what dictates it. So, what is the molecular basis? So, when pi electron system approaches closer and when center to center distance becomes less than 4 angstrom. So, in those cases what happens, the overlapping pi and electron density, pi and electron density partially cancel each other, right. So, and dipole moment interface destructively contributes now, constructively means add ho jayega, will go up, destructively it will reduce. So, net result what will happen? The decrease, right, oscillator strength and this molar extension coefficient like epsilon value. So, that means absorption जो भी A that will reduce because of this. So, when we go to unfolding or denatured state, in those case aromatic amino acids becomes free and hydrated. So, at 280 that is a additive one, right, and hypochromia is 0 baseline, but partially unfolded some stacking of pi happens, some stacking of pi happens. Because of that there is a reduction in the molar absorptivity at 280, that is a 5 to 15% hypochromia happens. If it is natively folded, lots of optimized stacking happening, right, because it has to stabilize all the forces for having a stable structure. Therefore, essentially what happens, that reduction in the absorption happens 60 to 85%, that means 15 to 40% hypochromia happens. And when it goes to aggregated state, the stacking that is happening is extensive and therefore, lots of reduction happens like a 40 to 60% reduction in absorption happens, right. So, looking at these, what we can, looking at hypochromia index, one can calculate how much is in the folded, unfolded or aggregated state, right. So, essentially one can quantify it like a H1 fully unfolded random coil, then partially unfolded structure, molten globule or native structure or aggregated structure. So, this basically dictates the protein unfolding that can be measured at 280 change, right. You can do some simple experiment, you just heat the protein using temperature. So, like a thermal denaturation, you go from native to unfolded, or you can even come back renaturation, you can do that. So, progressive, that what happens for many protein, progressive increase in 280 happens as the structure unfolds, right, because unfolding happening. So, stacking is getting removed and therefore, absorption is increasing. So, loss of this hypochromic effect as the aromatic residue dissociates. So, at delta 280 absorption is change in the hypochromia. So, one can have it experiment like this 25 to 40 degree, it is native structure, absorption is low, compact aromatic stacking. As you increase the temperature, say we go from up to 55, this transitioning is happening. The absorption is increasing, but not completely, intermediate state, and that is a partial unfolding. When you go to 55 to say 70 degree, it is unfolded states, and now absorption has increased quite a bit, it is a high, and that determines the random coil or no stacking structure. And if we are more than 70 degree, this goes to aggregated state, it is a variable and it may decrease like if the precipitate forms. So, aggregation can also precipitate protein out of the solution and therefore, less absorption is happening, right. So, now what is the thermodynamic principle, right. So, we did already the denaturation and we studied that how we can study looking at the change in the absorption of the protein, right. So, change in the absorption of a protein. So, we can calculate now a stability, right, thermodynamic protein stability and delta G. So, what experiment we are doing? Taking a protein, putting in a cuvette and in the spectrophotometer we are heating it up by Peltier or something and monitoring how much absorption is coming. That is the experiment simple we are doing, monitoring the absorption of a protein while we are heating it, right. So, what is happening if the protein is in folding into a state, means it is going from native state to unfolded state. So, native state N, unfolded state U. At any equilibrium we can write it delta G equal to RT ln Q equilibrium, Q equilibrium U by N, and you can find it out equilibrium constant. So, that will be K equilibrium concentration of unfolded state divided by folded state. So, at room temperature 288, if delta G is, say delta G is positive, that native state is favored. If delta G is 0, that means equilibrium state, melting condition, and if it is negative, unfolded state is favored. So, all those conditions we can find it out, and one can find it out. The delta G negative, spontaneous unfolding, unstable protein. Delta G 0, equal number of native state and unfolded state. And this happens at the Tm temperature. If delta G is positive, that means native state is favored and its protein is stable, right, at room temperature. Similarly, you can have a cold denaturation. You can put protein in cold condition, 4 degree, room temperature, body temperature, fever temperature or very high. What happens? Delta G effect is most positive, right, and highly stable. If you go below even 4, now that you remember, this is the protein stability curve. So, here it is more stable. If you decrease from here, it unfolds again, that is called cold denaturation. Here you go again unfolds, that is heat denaturation. So, all the protein has some optimal temperature where it is stable, right. So, typically we store protein at 4 degree, it is the most here delta G is most positive, highly stable. At room temperature it is positive, stable. At body temperature it is a lower positive, moderate stable, but in fever condition it is a near 0 and partially unfold, and very high temperature your negative and complete unfolding happens. So, just remember, we are at body temperature, we are having our protein at a moderate stable, but you see our protein does not exist individual, उसके साथी दोस्त भी हैं body में, right, that makes protein stable. But when why you become weak, right, when you are in fever condition, your protein are going to partially unfolded state, which is not good because your muscle works on protein and they are not in optimum condition, that means they are going into some partial unfolded state. So, looking at these protein stability, we can learn a lot about disease condition, the health condition and all those. So, at any high temperature, stability is in question of a protein, right. So, now melting temperature and stability determination. Melting temperature versus thermodynamic stability marker, one can have it. Tm is the temperature where 50% of protein is in the denatured state, right. So, Tm is when the concentration of native state is equal to concentration of unfolded state. So, K equilibrium is 1 and delta G is 0. Now, one can have a determination of thermal denaturation from here. So, what kind of experiment we are going to do? Method 1, we can directly observe, observation we can do, midpoint method. So, record the absorption of protein at 280 versus temperature and identify absorption baseline, like a simple we are doing, we are measuring the absorption like this, right. So, here is a absorption at 280 and this is our temperature. We are doing this experiment. So, identify the baseline, this baseline native state, this baseline unfolded state, and then here is a 50% unfolded folded. So, this is our Tm, that is the first method we are doing. The second method we can do first derivative method. So, right, wherever the you put it like this and wherever the so maxima. So, you are now plotting dA by dt, dA by dt, and wherever the maxima point comes, that is a Tm. So, another peak we can do enthalpy change. The third method we can do, we can calculate the fraction of unfolding and fraction of folding at each temperature, as we say, right, at here fraction here most stable, as we go some portion is unstable, more portion is unstable, more portion is unstable, completely unfolded. So, each temperature is a like a equilibrium between some folded, some unfolded. Here folded condition, folded concentration is more, unfolded is less. Here unfolded is more, folded is less, and in between variable mixture. So, that one can find it out. Fraction of unfolding, that will be absorption A in a native state divided by A in unfolded state minus A in native state. So, at Tm it will be 0.5, that is what one can do it. So, thermodynamics relation at Tm, what is happening? Tm at Tm delta H divided by delta S, one can rearrange it, and temperature dependence Van 't Hoff calculation one can do, and one can simplify to find it out delta Cp. So, all these thermodynamics calculation that can be discussed in a separate thermodynamics course, you can find it out. At any temperature, the free energy will be equal to the enthalpy at Tm multiplied with Tm minus T divided by Tm minus delta Cp, that is a heat capacity, and then you can calculate it. So, some thermodynamics jugglery you can find it out, the stability of protein at any temperature, right. So, yeah, so what we looked at today is mostly how you can do a simple experiment for finding it out the stability of a protein at different concentration and in different state, right. So, I will take this discussion forward in the next class, and we will continue to do some more thermodynamics of protein stability and protein storage condition at various temperature. So, thank you very much and look forward to have you in the next class. Thank you.